All right, chapter 4 of the Law of Running is focused on temperature regulation during exercise. This is a great topic, and this chapter is packed with information. And I really enjoy this topic because of exercising and doing races in hot environment is really common for us who live in the Southwest. And so it really is a neat topic to go through. I'll tell you that this presentation is really geared towards understanding exercise and endurance performance in hot environments. Now, I'm originally from upstate New York, and if I was teaching back in upstate New York, I probably would have a bias towards understanding exercise in cold environments. But we don't have that here. Well, maybe we have 1 or 2 days that are cold, but really nothing bad here in Las Vegas. We've got to figure out how to exercise and maybe do a race in 100 plus Fahrenheit degrees for an endurance event, maybe even hotter. And and so I'm really interested in understanding the physiology behind that, what causes core temperature to go up or what causes someone to stop exercising when exercising in hot environments. So this chapter has lots of information, as I said. I'm going to break it down into 4 parts. Part 1, we'll talk about heat balance. Part 2, we'll talk about what affects heat balance. Part 3, we'll talk about preventing heat impaired performance. In part 4, we'll talk about the unfortunate incidents of when people die during exercise or during an endurance event. And we'll talk about maybe how to prevent some of that. All right, so exercise in the heat, exercise in a cold, bottom right picture. Really important to understand what clothes to wear during different exercising and doing endurance events in different environments, what to eat, what to drink during different exercise in different environments. And either an athlete needs to carry his or her own fuel or fuel fluid, or an athlete needs to take advantage of whatever aid stations might be present during an endurance event, and to make sure that they're taking in the right type of hydration on top of the right amount of hydration. So we got to get a main hypothesis going here to set up the stage for this, going through this material in this chapter. Main hypothesis for this chapter is the exercise in the heat is limited by rising body temperature. If your body temperature gets too hot, you're going to stop exercising. That's the main hypothesis that this chapter is based on. The other thing that's important here is ingesting fluid is an important mechanism to keep body temperature controlled and or maintain proper blood volume. Okay, so notice I didn't use the word dehydration there. Exercising in the hot environment, we need to take in fluid in order to maintain core temperature. Now, we've got to be careful because there is a trade-off to ingesting too much fluid, and I'm going to talk about this in later slides, but you carry extra weight, you may have GI problems, or hyponatremia, which is something that we should all know about, especially exercising in hot environments like we have here in Las Vegas. Excess weight, that obviously is the weight that you're either carrying with the fluid, or that once you drink the fluid, it's inside you and you have that excess weight. Okay, core temperature, heat balance is what we're interested in. Why do we get hot during exercise? Well, partly because of the transformation of chemical energy to mechanical energy. And more specifically, this transformation of chemical energy to mechanical energy is not 100% efficient. In fact, it's about 30 to 33%. So about a third of the chemical energy gets transformed to mechanical energy, roughly, okay? What does that mean? That means if I have 100 units of chemical energy through the aerobic or anaerobic metabolic pathways, I'll end up with about 30 units of mechanical energy, right? So where's the other energy go to? Well, that other energy goes off into heat. So the vast majority of the chemical energy that's being transformed to mechanical energy is being released as heat. So that heat is going to have to go somewhere. Think about your car. You know, if you drive your car for a while and you get out and put your hand on the engine's hot. Why is it hot? Because the transformation of gas to mechanical energy, so chemical energy to mechanical energy in the car, is not 100% efficient. In fact, it's probably less, the engine is probably less efficient than a human body. A car may only be 20, 25% efficient in taking the energy stored in gas and transforming it to power the car to go forward. The rest of that energy is transformed to heat. That's why you have a radiator. That's why you have a fan in the car to try to keep the engine cool. If your radiator goes bad, your engine will likely overheat and your engine will stop working. Same analogy, or that analogy works well for the human body. If our human body gets too hot, our radiator will our internal organs, our internal computer will tell our body to stop exercising. All right, and that's all has to do with heat balance. So let's keep going. Human body range must stay within a narrow range of temperatures, probably 35 to 40 degrees Celsius. Okay, now normal body temperature is 37 degrees Celsius or 98.6 degrees Fahrenheit. Now, there's lots of variability in that. If we take all of your core temperatures right now, you're probably going to be right around 37 degrees Celsius. Maybe some of you will run a little bit cold, maybe it'll be 36.8. Maybe some of you will run a little bit hot, and maybe you're going to be 38.3. So there's some variability in resting core temperature. All right. But in general, we say core temperature is about 37 degrees Celsius, and you have to stay within a pretty narrow band of temperatures to be healthy. As I mentioned, muscle contraction has an efficiency of about 30 to 33%, which means a lot of energy, the vast majority of the energy when transforming chemical to mechanical is being released as heat. Endurance performance is affected by the ability to get rid of that excess heat in a hot environment, or if you are in a cold environment, the ability to retain that heat. All right, so you either need to retain it if you're in a cold environment to maintain core temperature, or you need to get rid of that heat in a hot environment. There's lots of sources of heat, not only from muscle. So the sun is providing solar radiation that's hitting the runner. You have ground thermal energy. The ground has a temperature, and that ground thermal temperature is being radiated to the person. Reflective solar radiation off the ground, again from the sun. That's all external. We also have muscle generating heat. That's that conversion of chemical energy to mechanical energy. Now we do have some mechanisms to get rid of heat, and the primary mechanism that we're going to focus in on is evaporation due to sweat. That's why you sweat. You sweat such that evaporation helps reduce the heat on the skin of the person. And that reduction of skin temperature will ultimately help keep core temperature within a particular range. You also have evaporation through respiration. So if you're breathing and you breathe out, you can breathe out some of that hot air. And you know that when you're on a cold day, you try to warm your hands up by blowing in them. Okay. That is, you're trying to take the core temperature air and blow that on something that's cooler. All right, so lots of sources of energy, heat coming into the body, not just muscle, but the big thing that we're going to be talking about is muscle. And this ability to lose heat and evaporation is going to be partly a function of this environment as well. And we've done some work on this. To do this type of research, we actually have people swallow a core temperature pill. It looks like a big vitamin. And that core temperature pill goes down into the stomach, then it goes into the GI tract. And once it's in the GI tract, we can measure really well the core temperature. And we've done work where we've looked at core temperature while people are swimming in different wetsuits and in water of different temperatures. I don't know if you recognize this picture, but this is the Colorado River. And this is Willow Beach, okay, Willow Beach. And we went down and collected some core temperature while swimming in that water. And that water is cold. That's 55 degrees Celsius down there. And so we were able to monitor core temperature. Here's resting core temperature right here. Swimming in wetsuit 1, core temperature went up in the 55 degree Celsius water. Then we changed wetsuits, swam again in a second wetsuit, core temp went up again. And then we swam a third time with no wetsuit and core temperature went down. It's going to go down because the water temperature was cold, 55 degrees Celsius. So in the cold water, we're giving off a lot of heat, but in a wetsuit, we're able to retain some of that heat. And so this has been some neat work. We've been continuing on this project, and we're doing some work swimming in wetsuits in warmer water. And interestingly enough, in the warm water, we have not seen a rise in core temperature. And this is an interesting thing that we're trying to look into right now. Why is core temperature not going up while swimming in warm water? We have some ideas. It may be methodological in that cooler water is getting into the wetsuit during swimming in the pool. It may also be a central governor model issue. And that being that the person is going to pick a swim speed that does not allow core temperature to go up. So this is a fun project, and that's the pill right there, by the way. Okay, so heat balance. This is all talking about core body temp is all predicated on understanding heat balance. The goal of temperature regulation of the body is to maintain a near constant core body temperature. That's homeostasis. So heat loss must match heat gain, okay, or vice versa. A function of the circulatory system is to transport heat. During exercise where heat must be lost, the blood flow is increased to the skin, and it gets that blood flow closer to the skin, and heat will always flow from hot to cold. And if we could get the blood flow nearer to the skin, it can be nearer to the environment. And as long as the environment is cooler than the skin temperature, the heat will leave the body. During exercise where heat must be retained, blood flow is directed away from the skin, and we have vasoconstriction to the skin. That's why you might get frostbite. If you're really cold, your body will shut down blood flow to the extremities and trying to maintain that blood flow closer to the core. So this is just a little cartoon, 37 degrees Celsius, what we're trying to maintain. This is a balance scale. Heat gain from muscle, environment, even metabolism generates heat, heat loss, sweat, environment, respiration. This has to be balanced in order to keep the body at 37 degrees Celsius. How does this happen? Well, temperature regulation in the human is done and controlled by the hypothalamus. There's just a picture of where the hypothalamus is. It's in the roughly the center of the brain, and it works like a thermostat. That's what its job is it monitors core temperature. And if core temperature starts to go up, it's going to signal certain changes to happen. If core temperature goes down, it's going to signal other changes to happen. And that's what this graph over here is showing. So if we have a heat load, if the hypothalamus detects increase in core temperature via thermal receptors at both the core and at the skin. So it's not just blood flow around the hypothalamus, it's getting information from the core of the body, as well as from the surface of the skin or near the surface of the skin. That information goes to the hypothalamus, and then hypothalamus for a heat load will allow for vasodilation. It will shunt the blood to the surface of the skin, and it will also promote sweating. Sweating is an important mechanism for keeping the body cool. Fluid is it is sweat gets on the surface of the skin, and that sweat has to evaporate for the skin to get cooler. And if you can keep the skin cooler, then the core temperature will stay cooler, because heat will always flow from warm areas to colder areas. So if the core is hot, you can cool the skin, the heat will flow away from the core to the skin and ultimately to the environment. In a cold environment, if we're exposed to cold and core temperature starts to go down, again, receptors from the core and from the skin, that information gets fed to the hypothalamus, and now we have shivering. Shivering is a very effective way to increase core temperature, because you're generating a lot of heat due to muscle contraction. Vasoconstriction, so now you're having blood flow not towards the skin, but now you're trying to keep blood flow near the core, and you're trying to maintain the warmth of that blood at the core. All right, so the hypothalamus really is the critical structure, and just like your car has a temperature gauge. In essence, your hypothalamus is your body's temperature gauge. If it goes hot, it will do one thing. If it detects going cold, it will do something else. All right, so I've said this a few times, but heat transfer, energy can be transformed from one form to another. We don't really have heat production or heat loss. Those are descriptors of transforming energy from different forms. And really, transformation of energy from one form into another is chemical to heat. That's part of the process that we're breaking down carbohydrates and fats. We want the mechanical energy, but that's not 100% transforming 100% chemical energy to mechanical energy. So some of it goes off into heat. Transfer of energy from one object to another, heat gradient. Heat will always flow from objects with high temperature to objects with low temperature. Always, okay? Always going from high to low. The body produces heat through normal metabolic processes. Not a large amount, but when you do eat, that does require metabolic energy, and that ultimately will generate heat. Voluntary muscle contraction, this is a big part, and we're going to see some factors related to this. Heat results from contraction of the muscle. Involuntary muscle contraction, and that's the shivering that I mentioned. Shivering can increase heat production as much as 5 times resting. So it's really an effective way to stay warm. All right, so mechanisms of heat loss from the body. And these are good mechanisms to know. Radiation is heat loss to the environment in the form of infrared rays. There's no physical contact. So we get radiation from the sun. We also can radiate heat to the environment. Conduction, heat flow from cooler object to hotter object where the objects are in contact with each other. So you're conducting, you're touching one object to another. If I grab an ice cube, heat will flow from my hand to the ice cube because the ice cube is cooler. Convection is a form of conductive heat loss. So there is some type of contact, but it's a little different. Heat is transmitted to the air or water molecules and moved away from the heat source, for example, a fan. So really the conduction part is the contact with the air or water molecules, but convection is the circulation of that heat to the air and water molecules, and then those molecules get moved away from the body and carry heat away. Evaporation is the change from liquid state to form to vapor. Heat is transferred to the skin via water. When water has reached sufficient heat, it is converted to a gas, and that's the evaporation. And that evaporative process is what's critical to the sweating mechanism. If the sweat does not evaporate from the skin, then the sweating is not effective. This is a big issue in exercise in humid environments. When humidity is so high, and humidity describes the amount of water vapor in the air. When humidity is really high, the sweat cannot evaporate from the skin, and therefore sweating becomes very ineffective at getting rid of heat. This is partly why it's really hard to exercise in hot and humid environments. These are just some pictures of different ways to get rid of heat. So here's the radiation from the fire, no contact. Convection is convection is the hot part of the pot contacting the water molecules, and then the water molecules moving away from the hot part of the pot. So that would be convection. Conduction is the touching, the contact between, in this case, the hand and the handle. That would be conduction. All right, so summary of part one. It's all about heat balance. Core temperature, we want to try to maintain right around 37.1 degrees Celsius, 98.6 degrees Fahrenheit. And we have to have mechanisms in the body to manage any heat load, where the heat is being delivered to the body, either through sources external to the body, like the sun or the surface, or internal in terms of muscle contraction. Okay, thanks.